So we're going to move into chapter 2 now with this next video. So the next 3 sections that are all encompassed in chapter 2 are all about exponential and logarithmic functions. So what I decided to do first is in section 2.1, we're not going to really do any calculus right now, but what I want to spend this time going over is some review material of what you should have covered in an algebra class. But in case you haven't seen it in a while, this is a chance to kind of get everything back under your belt. So section 2.1 is titled Exponential and Logarithmic Functions of the Natural Base E. So as you can see from the title, we're going to focus mainly on base E stuff when it comes to both of these topics. There are other logs and exponentials you can do, but that's the ones we're going to focus on. So recall from algebra that an exponential function is given by a function of the form f of x equals a raised to the x, where a is bigger than 0 and a cannot be 1. The number a is what we're going to call the base of the exponent. Every exponential function, as you should remember, has a y-intercept of 0, 1, because if you raise any base to the 0 power, it's going to be 1 in this case. It will not have an x-intercept because exponential functions don't equal 0 ever. And the function is continuous for all real numbers. So, while the base of an exponential function may be any positive number except 1, we find that in calculus, a special number called the natural base is actually more useful. So the natural base that we're going to work on is actually denoted as E. And this may be a number you're familiar with. It's on most calculators that people use nowadays. So the official definition that you don't really have to know, but I decided to put it on here. E is equal to the limit as n approaches infinity of 1 plus 1 over n to the n. You'll never have to use that definition, but I wanted to put it on here. What you probably remember is that E represents this long transcendental number that goes on forever and ever and ever. So the first few digits are 2.71828182845 ... Big thing to remember here is that E is the natural base, and it equals a number that's a little bit less than 3 if we ever need that for an approximation purpose. Hopefully you remember the basic idea of graphs. So if not, here's a quick little review. When you are graphing exponential functions, there's 2 different ways this can be done. It's dependent on whether the base is bigger than 1 or if the base is between 0 and 1. If the base is bigger than 1, so if your a value is any number bigger than 1, your exponential function will be what I like to call an increasing exponential function. So as you can see, there are no x-intercepts. So it's going to start really, really close to the x-axis way over here. And as you move to the right, it's going to increase. It has to cross that point 0, 1. And then it increases very, very quickly once you move into the right-hand side of your graph. If the base of your exponential function is between 0 and 1, so something like 1/2, then when you graph an exponential function like that, it will be what I like to call a decreasing exponential function. So this time, though, you would start very, very high on your graph on the left-hand side, and you're going to decrease very quickly until you get to the point 0, 1. So both graphs have the same y-intercept. As you get past that y-intercept, your decreasing definitely slows down because you can't cross the x-axis, and it will slowly move to the right and get really, really close to the x-axis. But remember, it can't touch it because there are no x-intercepts with an exponential function. So let's do a couple practice things from algebra. If I give you the functions y equals 2 raised to the x plus 1, I want you to sketch this graph, and then can you identify the domain, the range, the y-intercept, and whether it's an increasing or decreasing function. Now, we're actually going to be able to answer the last question first because that's kind of how I base all my exponential functions. So first thing I see is that we have an exponential function, at least initially, of 2 to the x. Since your base a is 2, and that is a number that's bigger than 1, I automatically know this is going to be an increasing exponential function, guaranteed. The thing that's extra here is this +1. If you remember from algebra, when you have a number being added on the outside, and we reviewed this on, I think, the very first section, this is called a vertical transformation. So what it's going to do is it's going to take your normal exponential function that we just went over, and it's going to move everything up one spot. So that means your y-intercept, which is normally at 0, 1, is going to move up to the point 0, 2. So that kind of answers the y-intercept question. I know it's going to be increasing. Now, in a normal exponential function, you can't cross the x-axis. But since everything has to get moved up one spot, what ends up happening here, I'm going to try my best to draw this as I can. Use my little tools here. You are going to actually have, sorry, I hit the wrong button. You're actually going to have your axis moved up by one spot. So it ends up looking something like this. So once again, all I did here is I took my x-axis and I moved it up one spot just to kind of give me an idea of what I can't cross. And then my graph will just be a nice increasing exponential function. Now, in the real problems on your homework, that dotted line will not be there, but I'm using it as a reference to know how high and how low the graph can go. So now the only two questions I haven't answered yet are domain and range. So we'll answer those over here on the left-hand side. So remember, domain is all of the x values of your exponential function. And here's the good news. The domain of every exponential function is everywhere. It will always be from -infinity to +infinity because you can plug in any x value that you want. The range is the set of y values, and this will not be everywhere. So you have to look at your graph and find the y values of which it exists. Now, here's another good reason for having this dotted line. Since you're going down on the y-axis, the lowest this graph will ever get is at y equals 1. Now, I'm not going to include that because there's a dotted line that we can't touch. As you go to the left or as you go up, you see that your graph goes up forever. Since the graph will increase forever, you will never be able to find the maximum y value, so we call that infinity. And that would be your range. Just remember that domain, you are looking at the x values, and range, you are looking at the y values. So we sketched the graph, we found the domain and range, and then we found the intercept, and then whether it was increasing. Just so you can see a second one, let me do one more just like that, but I'm going to move into our natural base instead. So I want you to, once again, sketch the graph of y equals e to the x minus 2. I want you to identify the domain, the range, the y-intercept, and whether it's increasing or decreasing. So I'm going to do this in the exact same order we just talked about. So number one, the base of your exponent is e. So if e, which we know is about 2.71, that is obviously a number that is bigger than 1. So I automatically know that my graph is going to be increasing. This -2 on the end is another vertical translation, which means that your whole graph has to be shifted down 2 units. So that actually, once again, affects our y-intercept. Normally, your y-intercept would be at the point 0, 1. But if you shift that down twice, it puts you at the point 0, -1. So that will be the answer for our y-intercept. As we saw a second ago, this also shifts that the axis that you can't cross. Normally, it's the x-axis you can't cross, but if we're shifting everything down 2 units, that means we're not going to be able to cross now. I'm a little off here, but that's okay. We can't cross at y equals -2. So I shifted that down just from my reference point. Then I'm going to draw an increasing exponential function. So it looks something like this. So there's my rough sketch. And from this graph, we can once again now easily find what the domain and range are going to be. Just like number one, don't sweat too much on the domain, because the nice thing about exponential functions is that they always have a domain of negative infinity to positive infinity, all real numbers. If you look at your y-axis to find the range here, your range is going to end up being the lowest y value you get to is -2, which we don't include because we can't touch that imaginary line there. And then if you go up, you can see once again that your graph increases up forever. So it will once again have a range all the way to infinity. So your final range is from -2 to infinity. We found the y-intercept and we sketched the graph as well. All right. Another thing you probably covered in exponential functions was compound interest. This is kind of our business application of this section. So if you need to pause the video to write this formula down, please do that. I'm going to talk a little bit here on this slide before I move on, but you can pause at any point. So there are two compound interest formulas, and as you can see them both at the top, I'm going to break them down both individually. These are formulas that we can use to figure out how much money you will have in an account based on certain parameters. Now, the one on the left has a lot more variables that I want to run through with you. So if you have A equals P times 1 plus R over N to the NT power, A is your final value. That's usually what we're looking for, but not always. P is the amount of money that you're going to invest. So however much money you put in your savings account to start off. R is your interest rate as a decimal. So remember that if you had something like 2%, you have to divide it by 100, or some of y'all may have learned move your decimal to the left twice. Either way, you have to always convert your percentages into a decimal form. So 2% would be 0.02. T is the amount of time in years you're going to leave that money in. And then the number that might fluctuate is how much your compounding frequency is affected. So if N is your compounding frequency, there are 5 of them that you're going to see in this class. So let me run through those. If you see the word annually, you're going to let N be 1, so 1 time a year. Semi-annually means it happens twice a year, so that's N equals 2. Quarterly is 4 times a year. Monthly is 12 times a year. And then if you see the word daily, that is N equals 365. And you would plug your numbers into this formula and then use your calculator to figure out the value. Now, this formula over here on the right looks a lot nicer. That's because it only happens if one thing is true. If you see in the problem that your interest is compounded continuously, then you can use the formula above, which is A equals P times your natural base E raised to the RT power. Now you have a lot less letters to worry about here, but they all mean the same thing. P is still the amount of money invested at the beginning. R is still your interest rate as a decimal, and T is still the time in years. The only difference is you don't have an N value, because since you're compounding nonstop continuously, you don't have to worry about it. It's built into the natural base of E. So let's do an example here to see how much it's affected. So I want you to find the future value of an investment of $75,000 when interest is 4.5% for 3 years and is compounded in the following 3 ways: monthly, daily, and then we'll do one with continuously. Now, monthly and daily are going to use the same formula, but we're going to have one value that's different. So for both of those, we're going to use the formula A equals P times 1 plus R over N raised to the NT power. And if I label the values in the problem of what these are, your $75,000 here, oops, sorry, my pen lagged for a second. The $75,000 you see here is your principal value. That's how much money you're putting into your savings account, we'll say. The 4.5% is your interest rate, but remember, you can't use 4.5. You will have to move your decimal to the left twice, and we'll use 0.045. The 3 years over here at the top right, that's going to be your T. And then what's different about A and B is what N value you're going to use. So for part A, if you're going to do something monthly, you have to let N equal 12. Versus on part B, when we do daily, we're going to have to let N equal 365. So from here, this is more kind of a calculator problem. So we're going to plug these numbers into our formula. Let's start with monthly. We would say A is equal to 75,000 times 1 plus your interest rate, which is 0.045, divided by N, which is 12, raised to the N times T, which is 12 times 3. And like I said, if you need to pause the video at any point to try this yourself, I'm going to type this into my calculator. And since we're doing a money problem, we're going to round to the nearest cent. So this would be $85,818.59. So it looks like you would make a little over $10,000, almost $11,000 in 3 years based on this information. Let's see how much it's affected when your N is 365. So the problem will look very similar. You will take $75,000, multiply it by 1 plus. Your interest rate doesn't change, but what does is this 365. So we'll divide your number by 365 instead, and then raise this to the 365 times the same T value, which is 3. Once again, I'm going to type this into my calculator. And I got a value of not much different. It is $85,839.54. So as you can see, the number of times you compound doesn't really make a huge difference. So based on this, if you compound every day versus every month, you'll make about an extra $21 over 3 years, which is not really a big deal. Now at the bottom here, it says we're going to compound continuously. So this is a different formula because there is not an N value. So when you compound continuously, you're going to use the formula P times your natural base E raised to the RT power. And if I plug the same numbers into this formula, we will say A is equal to 75,000 times, wrong formula, times E raised to the interest rate, which is still 0.045, times your T value, which is 3. So do make sure that you can find the E button on your calculator because that will be necessary. So if you don't have a calculator that has that, you need to make sure you get one because you won't be able to do the problems in this section without it. So when I type this into my calculator, and if you did it yourself, I got $85,840.26. So as you can see, even compounding it nonstop only made us an extra 75 cents compared to doing it daily. So very good. This is how you'll work your compound interest formulas. All right, so we reviewed exponential functions. So now let's review logarithmic functions. So if you remember the regular logarithms that you did in algebra, those are great. You can still use those. We're going to primarily focus on the natural logarithm because that's the one that has better calculus ideas. So let's just go over that. For any positive number x, the natural logarithm, or also known as a logarithm of base e of x, is given by the following formula. Natural log of x, which we represent as ln of x, is the same thing as doing log base e of x. Now, this natural log formula is very important because it's a direct relationship to our exponential stuff we just reviewed. So if you have the equation y equals the natural log of x, it can be converted into an exponential function of the form e to the y equals x. What you might remember from algebra is that logarithms and exponential functions are inverses of each other. So when ln's change to e's, your inputs and your outputs switch. So you can see that the input of a natural log becomes the output of an exponential, and then vice versa with the y values. Now, the big difference we're going to see is that the domain of a logarithm is different than the domain of an exponential. We kind of got a little bit lazy early because we could do that. Exponential functions have a domain of everywhere. With logarithms, they only can use an x value that are positive, because you cannot plug negative numbers and you cannot plug the number 0 into a logarithmic function. So what we can say is that if you're finding the domain of a logarithmic function, if it's not altered at all, it would just be from 0 to infinity. Now we'll see some examples in a minute where it's altered a little bit, and I'll show y'all how you can find your new domain. So let's practice that actually. So number 4 and number 5 say find the domain of these natural log functions. So number 4 has the function y equals the natural log of 5x minus 2. Now, since the inside of your logarithms have to be positive numbers, if you're trying to find the domain of something like this, remember, this has got to be positive. And what you should remember is that in mathematics, how we represent positive numbers is we can say that 5x minus 2 must be greater than 0. Remember, it cannot equal 0 because you can't have a 0 inside the logarithm. If you solve for x here, so if I add 2 to both sides, 5x would be greater than 2. And if you divide both sides by 5, you will get x is greater than 2/5. And when you write that in interval notation, that would be from 2/5 to infinity. And that would be the domain of this logarithmic function. Where you've got to be careful is a certain algebra property that might cause you to flip some stuff around. So let's look at number 5 to talk about that. What is the domain of f of x equals the natural log of 9 minus 4x, and how does it be different than the one we just did? All right. So you're going to start it off the exact same way. The inside of your logarithm has to be positive. All right. So if I take the 9 minus 4x and I set that greater than 0, let's see what's different about this one. When you subtract the 9 over, you get negative 4x is greater than negative 9. And as you hopefully remember from an algebra class, is that when you divide by a negative number and you're dealing with inequalities like greater thans and less thans, when you divide by a negative, it flips around your inequality and then you simplify the other side. So a negative divided by a negative is a positive, so that's positive 9/4. If you write this in interval notation, since it's less than, your interval would actually be negative infinity to 9/4. That is the domain of your natural log function. All right. We reviewed graphing of exponential functions earlier. Probably not as common, and we really don't do a lot of graphs of these, but we need to make sure we know at least the basic graph of a natural log function. So as you can see over here on the right, this is what a graph of the ln of x function looks like. So it looks a little bit inverted from an exponential function, which that makes sense because they're inverses of each other. Couple things to note here is that logarithmic functions, where exponential functions had a y-intercept of 0, 1, natural logs have x-intercepts instead, and usually it will cross the point 1, 0. The other thing to note is that since logarithms can't be 0, you can't plug 0 in and you can't plug negative numbers in, you'll notice is that as you move towards the axis, my arrow's kind of off here a little bit, but you cannot cross the y-axis because you can't use x equals 0 or any negative x value. Now that can obviously be changed if the inside of your logarithm becomes something different. So what I want to show you down here at the bottom is how would you sketch a logarithm that has more than just an x on the inside? So what I want you to do is I want you to take y equals the natural log of 3x plus 6. Let's find its domain and then see how that impacts what the sketch of the graph looks like. So just like number 4 and number 5, for the domain, I know that the inside, the 3x plus 6, must be greater than 0. Well, if I subtract the 6 over, 3x would be greater than negative 6. And if you divide both sides by 3, now remember, just because 6 is negative doesn't affect this. Since you're dividing by a positive number, x has to be greater than negative 2. So your domain would be from negative 2 to infinity. Now, how that affects the graph of your logarithm is this. Instead of it being the y-axis that you can't cross, the difference is now is that you would go over to the number 2, or negative 2, I'm sorry, which is what your domain says. And I'm actually going to shift my y-axis in that direction. Because now everything less than negative 2 I cannot use. I can use everything to the right of negative 2 all the way to infinity. And then as far as the sketching goes, we're going to draw a sketch just like the one above. It'll look something like that. That's not perfect by any means, but that gives you a rough idea of how you can sketch basic logarithmic functions. All right. The big thing, the graphing's nice, but it isn't the big thing. The big thing with logarithms, and this is, we're going to specifically talk about natural logarithms, is that there are some properties that help us simplify and solve certain equations. So we got a few rules here if you need to pause the video to write them all down, but I'm going to run through all 7 of these for you. So beginning with property A, if you have the natural log of 2 things being multiplied together, like m times n, you can break that up into the natural log of m plus the natural log of n. So multiplication breaks up into addition. If you have division, so if you have the natural log of m divided by n, division breaks up into subtraction. So this would be the natural log of m minus the natural log of n. So multiplication to addition, division to subtraction. If you have an exponential function or term inside your logarithm, let's say it's m raised to the k, then that k power, if you need to, and we will need to in a few minutes, you can bring that to the front and rewrite it as k times the natural log of m. So you can bring any exponential power directly to the front as long as you multiply it by the natural log. All right, so to the right, you're going to see a few properties of values that might help us out. So starting from the top on D, anytime you see a natural log of just the letter E, your answer will always be 1. As I talked about on the graph, but now we confirm it with our equation, the natural log of just the number 1 will always be 0. And that comes from the idea of it being an x-intercept. Rules F and G are cancellation properties from algebra. So remember that if you take the natural log of e raised to the x, as long as this ln and e are applied right next to each other, they cancel and you're just left with the x value of the problem. This also works going the other direction as well, except that since e is an exponential base, it has to be written in the following form. If you have e raised to the natural log of x, as long as the ln is the first thing next to that e, they do cancel, and leave the x right next to it. If they're not next to each other in either one of these last two properties, they do not cancel each other. So you may have to find another way to solve that problem. All right. To get you familiar with your calculator for the next couple of sections, hopefully if you have your calculator, you can get it out to practice this. You need to make sure you can find your LN button because every scientific calculator should have one. It may be hidden somewhere, but there should be an LN button somewhere. So all I did here is I went through and I wanted you to practice typing some of these in your calculator, and we're going to round to 2 decimal places. So I'll do that as well. Like I said, feel free to pause the video if you need to go find your calculator or practice these yourself. So if I type in the natural log of 9 into my calculator, I should get an answer of 197, so that actually rounds up to 2.20. If I do the natural log of 3.33, this should give me 1.20. Now, number 9, you can either use your calculator, or if you notice, this is actually one of your cancellation properties. Since the ln and the e are applied right next to each other, they actually cancel, and your final answer is going to be 8. Now, if you forget that cancellation property, the perk is that you'll have your calculator, and if you type in the natural log of e raised to the 8, it should come out to be the answer 8. All right, so now that we've learned a little bit more about logarithms, let me show you how they can be used to solve for different variables in that compound interest formulas we covered earlier. So number 10 says, Robert wants to have $15,000 available in 5 years to pay for new siding on his house. The interest is 4.3% compounded continuously. How much money should he invest to have this money available? So the key thing I noticed as I read that problem to you is that we are compounding continuously. The reason that is so important is because that tells me which of the 2 compound interest formulas I have to use. So I'm going to have to use the one as A equals P times E raised to the RT. So now on all the problems up here, let's be careful about what everything represents. It says Robert wants to have $15,000 available in 5 years. So this 15,000 is not your P. This is actually your A value. That's the final number he needs. The 5 years, is going to be your T. All right. And we still need our R value. So the 4.3% is your interest rate. But remember, you have to move your decimal to the left twice. So we're going to use 0.043 in this problem. So if I plug these numbers into the formula, A is 15,000 equals P, which we don't know yet, times E raised to the R, which is 0.043, times my T, which is 5. So if I multiply those 2 decimals together in the E, this would be, 0.043 times 5, which is E to the 0.215. And to get this P by itself, I need to divide both sides by this exponential function. That would cancel those. And then when we divide this in our calculator, if I take 15,000 divided by E raised to the 0.215, and we round to the nearest cent here, this says that our principal value has to be $12,098.12. So that tells us how much money Robert needs to invest at the beginning so that in 5 years he will have $15,000 available to pay for the new site. All right, so let's do another variation of this. Number 11. Now I want you to find the amount of time for an investment of $75,000 to double when interest is 4.5% and is compounded continuously. Once again, there's that key two words. Compounded continuously means we're going to use the formula A equals P times E raised to the RT power. All right, going through my problem, let's see what I know. I'm looking for time t. So my unknown this time is t, which means I should know what A, P, and R have to be. All right, let's see. We have an initial investment of $75,000, so that is my principal. And while it doesn't officially tell you the A, it says you want to double it. So according to that, that means that my final value needs to be double that, which is $150,000. The interest rate is 4.5%, but remember, move your decimal over, and we're going to use 0.045 as our value. So let's plug our numbers into this formula and let's solve for t. So A is going to be $150,000 equals your principal, which is $75,000, times e to the interest rate, which is 0.045, and then we don't know what t is. So to solve for t, the first thing I would do is I would divide by the 75,000 in the front to get rid of that big number. And what we're going to see is a nice little ratio here. We kind of already know this. 150,000 divided by 75,000 is 2 because you're trying to double your money. Now, the challenge here is that this t is in the exponent of your base e, and we need to get it out of there. So the reason I went over those properties with you earlier is because I need to cancel this e or get rid of it. And the only way to do that is to take the natural log of this e. So I'm going to apply the natural log of the right-hand side. But if you do something to one side, you will have to do it to the other as well. So I'm going to also take the natural log of 2. On the left-hand side, this doesn't do anything. This is just the ln of 2. But on the right, the ln and the e would cancel each other based on our properties, and we're left with 0.045t. Finally, if you divide both sides by 0.045, this cancels, and this is where you can get your calculator out. If I type in the natural log of 2 divided by 0.045, this means I'm going to need about 15.4 years for this money to double. So to take your $75,000 and make it double, you're going to need to leave the money in for a little over 15 years. All right, and last but not least, our last little, once again, review question for section 2.1. It says the price in dollars per unit that consumers are willing to pay for the Trailmaster mountain bike is given by P of X equals 980 minus 90 natural log of X, where X, key here, is in thousands of units. So part A says, what price corresponds to a demand of 150,000 units? Well, what a lot of students mess up here is that they will try to take the entire 150,000 and plug it in for X. That's not what you're supposed to do here. Since it says X can only be in thousands of units, you have to convert this. So you would take X is actually equal to the 150,000 you plan on plugging in, and you're going to divide it by 1,000 to get your ratio here. That's going to give you an X value of 150. That's the number you're going to plug into your demand function. So I'm going to find P of 150, which will be 980 minus 90 times the natural log of 150. And this is what you can type into your calculator. And that will give you an answer of 529.04. So that would be the price that you would charge for each mountain bike to get a demand of 150,000. So be careful, don't plug the whole number in. I'll put a big X here in case you look at the video later. You have to divide it by 1,000 because the last sentence says X is in thousands of units. Now, other way around, part B says, how many units will consumers buy at a price of $400 per bicycle? So now what they're doing is they're giving us the price. And we're trying to solve for how many units, which would be X. So I'm going to plug the $400 in for P of X in the original problem. So that's 400 equals 980 minus 90 times the natural log of X. So let's solve for X here. I'm going to first subtract 980 from both sides. So this would end up giving me negative 580 equals negative 90 times the natural log of X. I'm then going to divide both sides by negative 90. If you want to reduce this, you can, but you don't have to because we're going to end up using our calculator anyways. So one thing I am going to do is I'm going to drop the negatives off. So this would be positive 580 divided by 90. And then now we can go over that other cancellation property that you're going to need. The only way to cancel a natural log is to apply an e to it. But since the e has to be the base of your exponent, we have to do e raised to both sides. So this 580 over 90 actually becomes the exponent of e. Now on the left, the e and the ln cancel so that all you have is an x. And if you type this right-hand side into your calculator, you should get 629.197. Once again, though, that beginning problem is where everybody gets this problem wrong in my class. This is not your final answer. Remember, X is in thousands of units. So in order to get the number of units, you now have to multiply this decimal by 1,000. So when you do that, you actually end up with the number of bikes that you're going to have demand for as 629,197. And once again, I multiplied by 1,000 because I only solve for X here. But since X is in thousands of units and it's asking for how many units answered the question, that's why we multiplied at the end. So that ends the kind of review section of exponentials and logarithms. So we went over all the E stuff and all the LN stuff. In the next video, we're going to go back to doing more E stuff and we're going to do derivatives of exponential functions.